So in practical wireless sensor networks, so we're going to have the introduction, problem formulation, then we're going to go through the distributed self-decision fusion rule, and then quantized distributed self-decision fusion rules, and then finally it is the proposed two-step fully distributed detection. And then we're going to look to some simulation results, and then conclusion and future work. So distributed detection has been attracting a lot of interest in the context of wireless sensor networks. So I refer to these mainly two papers, Chamberlain 2007 and Barbarossa 2013. They're flexible and can be easily deployed over a wide geographical area to monitor and for monitoring and surveillance purposes. So there are challenges, of course, and here I mentioned two of them. The most important thing are they suffer from constrained bandwidth and limited onboard power. There are challenges in the design of distributed detection algorithms, especially when the intruder is unknown to the wireless sensor network. So this is the case which we are considering. So the objective is to improve the detection by taking advantage of spatially distributed information across a field in a matter that we utilizes the scarce bandwidth, overcome the limitation of fading wireless channel, and what is most important is to arrive at an optimum global decision across every sensor network in the network. Some strategies consider the centralized solution where there is basically a fusion center where the noisy observations are collected, and then the fusion center is able to compute the test statistic in a single shot. So these are the papers that you can have a look at. The recent publication, which is Gar and Faney 2014, considers sensor node collaboration in the context of distributed estimation, where the exchange of information among the sensor nodes is reported back to the fusion center. So the first part is there is no any sensor node collaboration, and there is a fusion center. Recently, they proposed some sensor collaboration, but again, there is a fusion center. Then we have the fully distributed strategies, which these are the references, Shiaz, Cativelli, Zhang, and Bertrand, where the sensor nodes exchange local information iteratively with their neighbors and are shown capable of reaching a global optimum decision across the field. So what they consider is ideal exchange of information among the sensor nodes, but it's not feasible in the context of wireless sensor networks. The sensors are battery operated, so they have limited energy on board. Practical wireless sensor networks suffer from channel impairments such as fading and attenuation. So what we've got, we have sensor deployed across the field, and we have a target which we're considering in this case a binary event, either 0 or 1, present or absent. And after the sensor nodes get the information, the test statistics in this case is the energy detector. Since the signal is unknown from the target, it reports to the fusion center. Then the fusion centers, in this case we assume equal combining, gets the final test statistics compared to a threshold and decides. So this is not what we're going to look at. We're going to look to a distributed solution. There is no any fusion center. Again, we have the target, we have deployed the sensor across the field. Among the sensor nodes, there is a partial inter-sensor connectivity, right? So it is to say that there is not a fully connected network. This sensor, for example, sensor node 1 and 3 communicate with each other, sensor node 3 and 4, but for instance, sensor node 6 and 5, there is no any communication link between them. So that's what we consider in this work. So again, as I said, we're looking to a binary event. So the signal is present or the signal is absent. So as we said, the signature signal is unknown at the sensor nodes. So what we deploy as a test statistic is the energy detector. So all the individual test statistic at the ith sensor node is the energy detector. So at the beginning, to make it clear later on, so if we assume ideally that all those test statistics are available at each sensor nodes, then if we combine them and get the final test statistic, so the fusion center, which is the centralized detector, takes this test, where lambda f is the detection thresholds. Okay? So if it is greater than that, it decides the target is absent. If it is greater than that, the target is present. So of course, if we consider the Neyman-Pearson approach, then for a fixed probability of false alarm, that's the expression for probability of detection. We explicitly state it in here because later on we'll have an expression, an analytical expression of probability of detection, which is a function of the some very useful parameters that we'll be looking at. But again, as we said, the sensor nodes have limited bandwidth, power, and quantization. So the problem with the fusion center and centralized have already been addressed in our previous paper, so you can have a look at it and see. So now what we're looking at distributed self-decision fusion rule. So there is no fusion center. Each sensor node is tasked with the detection, and they iteratively shares the current test statistic with its neighbors. So we grabbed some tools from the graph theory, which we model the interaction among sensor nodes by an undirected graph, where that capital V represents the set of M sensor nodes, and that epsilon is the set of the edges ij. So you can graph the graph properties by an adjacency matrix, where if that entry in that matrix is 1, it says there is a connection between the sensor node. If it is 0, then there is no any connection. So of course the delta I is the neighbor sensor nodes, and the cardinality number of neighbors is the magnitude of that. The Laplacian matrix, which is an important matrix that you can grab the properties of the communication topology, is defined as such. So remember these two matrices, because later on we'll introduce our proposed approach, and they will be in the algorithm very important. So yeah, so one way to look at distributed self-decision fusion rule is to have the consensus algorithm. So basically, at the ith iteration, at the ith sensor node at k plus 1 iteration, that's how the current test statistic is updated. And you run these for large number of iterations. So that type of evolution can be written in a matrix form, where W is an identity matrix and the Laplacian matrix that we introduce later. And that is an epsilon, which is a constant that we'll elaborate later. So distributed unquantized fusion rules. So having those test statistics at the ith sensor nodes at the kth iteration. So again, we can decide on the presence of the signal, but now at the ith sensor nodes, where this is the threshold at the kth iteration. So previously we had the test static at the fusion center, but now our decision is actually across the whole sensor node. So these are the means and the variance. And again, for a fixed probability of false alarm, consider the Neyman-Pearson approach. That's what we have the probability of detection here. And it is shown that for large number of k, this converges to the PD that we showed in the centralized approach, when there was a fusion center, and this now is without a fusion center. So when k is large, those two approaches to each other. But of course, as you increase the number of iterations, so each of the sensor nodes have to transmit at each iteration and hence dissipate its energy. So later on, we look how and where to stop at each iteration, such that we effectively get the global optimum decision, but of course we save some energy. The previous approach was assuming that the sensor nodes ideally communicate with each other, but that's not the case in practical. So that's why now we are looking to the quantized consensus algorithm framework with limited bandwidth. So what we propose is we propose a scheme where each of the sensor nodes I encodes the data using a simple uniform quantizer. So we also propose to establish a link. In other words, we actually establish the communication topology among the sensor nodes as such. If a known SNR at the ith sensor node is less than a threshold, so there is no communication between I and j sensor node. If it is greater, then there is a communication. So that is an SNR threshold parameter, and it is defined as such. This is the sensor transmit power. These are the channel coefficients. This is the AWGN noise variance at the decoding sensor nodes, and this is the physical distance. So we propose to quantize with QI bits at sensor node I before transmitting to sensor node J. And here we introduce the channel capacity, but again we make a trade-off between the communication links and the number of bits that we transmit. A larger threshold, which defines, actually this threshold defines the communication topology, introduces a slower information diffusion across the network. So we'll have fewer communication links among the sensor node, but the number of quantized bits will be higher. A smaller gamma means we'll connect a more dense or connected graph and dictates a faster information diffusion across the network, but allows less transmission bits. So there is actually a trade-off between how we select this optimum threshold, and the simulation result will be looking at this parameter. So with quantization, the time evolution of the consensus algorithm can be represented as such, where here is the quantization noise, which we didn't have in the ideal case. So assuming that each of the test statistics has the finite range and uniform quantizing, that's the variance of the quantization noise. So in matrix form, this is represented as such. This term here represents the quantization noise. So we have actually the quantization noise there, and we'll be looking, does the consensus algorithm converge or not? So again, we can make the test at the ith sensor node and decide if the target is absent or present. So these are the means and the variance, and we have this term here, which represents the quantization noise in the case where we introduce the quantization. So again, we have the detection performance, and we see how that does the detection performance converge to the centralized approach. So we have shown and we have proved that that is not the case. As the k increases, the number of iterations, so this variance blows up, and eventually probability of detection at ith sensor node will not converge to the centralized with a fusion center detection. But we'll show that there is a finite k where to stop. So that's the proposed two-step algorithm. So what we do, we'll run the quantized consensus algorithm to improve the local version of the test statistics. But now we'll terminate at k is equal to k1, where optimum value of that is going to form the simulation results. So we now have these test statistics. We do the test, and we generate a binary random variable, 0 or 1. So the second step is now how, since at the kth iteration, which is a finite number, at each sensor nodes will have different decision on the target. So what we need is to converge across the sensor networks. So we'd like to have, what we adopt later on is having those binary random variables. So we'd like to have a test statistic in such a way that if we combine those binary random variables, zeros and ones, if it is different than m, when m is number of the sensor deployed, decide the target is not present, otherwise it is present. So this is the final test statistic on the second step. So the problem is how to evaluate that in a distributed manner. This will be explained in this second step. So here we introduce this binary consensus algorithm, where now we share the random variable zeros and 1, and eventually this converges at k2 minus 1 iteration, which this k2 is a diameter of network, and we know the diameter of network, and hence we know where to stop the second step collaboration. So now we can easily show that those ik2 are 0, we can decide the target is absent, otherwise the target is present. Again, this is similar. So now the proposed algorithm requires K1 plus K2 iteration, where the conventional algorithm requires, it converges in limits, so it requires infinitely many iterations. So in the simulation results, we have a wireless sensor network with M sensor nodes. So these are the parameters for transmit power. This is the path loss coefficient. These are the channel coefficients, fading channel coefficients. We construct two topologies which we will use later on. These are shown in figure 4 and 5. This is the average SNR that we use. So these are the topologies that we are going to be using in the simulation results. This is for epsilon 72, which corresponds to 3 bits, and the other one is with 2 bits. So as you can see, 3 bits is sparser, 2 bits is more dense. So here we can show that as the epsilon varies, we have an optimum epsilon such that the probability of detection is maximized. As you increase the number of sensors, the global probability of detection improves for each of the cases. Here again, we have the receiver operating characteristic for different number of the sensors. As we increase the number of sensors, we can see that the detection probability improves. Again, in here, we have the centralized detector. We have the proposed two-step with an epsilon in there. And again, this is the first step iteration where to stop the algorithm. Sensor node 6 is taken here for comparison purpose because it has the best probability of detection among all the sensor nodes that we have chosen. Again, in here we have the centralized detector, and we have our proposed two-step, and this is the centralized with 2 bits. So again, this approaches the effective upper bound. We vary now the average sensor SNRs, and this is the global centralized detector, and this is our proposed two-step with K1 is 20. So effectively, we need just 20 iterations, and our algorithm converges to the centralized detector. So yeah, we relay the communication topology with a number of bits to be shared. We show that there is an optimum number of iterations to stop the first sensor node collaboration. When we choose K1 and these 2 parameters, so we can show that our approach approaches the centralized detector with the fusion center. So we require a finite number of iterations, what is the most important things. And yeah, we assumed equal combining strategy. Future work will have a similar approach with optimum linear combining. So yeah, thank you for listening.
Okay, Edmond, thanks. I was panicking a bit when I saw 44 slides, but you managed to get through them all. Well done. So we started about 5 minutes late, so just time for a couple of quick questions, please. Any questions? Okay, thanks. Thank you, Edmond.